As we had seen in the previous class, the transmission line, which is meant for transmitting the power from one place to another place, and the analysis of that transmission line by using an equivalent circuit representing the magnetic flux when the current flows through the two-wire parallel transmission line induces an inductor, represents an equivalent element as an inductor, and the losses associated with that is represented by a resistor. And as you are considering a two-wire parallel transmission line, two conductors separated by dielectric, which is represented as a capacitor in shunt, and the leakage in the dielectric is represented as a conductance, and all these elements we call it as a distributed parameters, which we are considering for a section of transmission line which is of length delta z, and we are giving the input at transmission line and evaluating after a section of transmission line the voltage and current parameters, and it is varied in space with respect to time as well as space, which is represented as z comma t, z indicating space and t indicating with respect to time it is varying. So to analyze this circuit transmission line, which is same as your circuit theory, by applying KVL and KCL. According to KVL, we write potential rise and potential drop across the each and every element which is in a closed path must be equals to 0 by applying KVL and KCL. According to KCL, at a node current entering must be equals to current leaving. By applying this KVL and KCL and imposing a condition as time varying voltage and current, real part of e power j omega t, voltage and current e power j omega t, and we will represent KVL and KCL equations variation with respect to the space, and by rearranging this KVL and KCL equation you can represent the differential voltage with respect to space as dV by dz, which is proportional to the series impedance, which we call it as a Z as R plus J omega L. And similarly, the current, differential amount of current along the space, which is represented as minus Y times of V of Z, Y indicating it is a shunt admittance. And these two equations we call it as a governing equation. dV by dz equals to Z minus Z into I of Z, and di by dz is equal to minus y into v of z. Here we have come across the two parameters called as series impedance R plus j omega L and shunt admittance G plus j omega. And we need to find out the solution for this governing equation as first order differential equation with the two different parameters it is. So convert that into second order differential equation by differentiating on both sides and substituting with other. We'll be getting a new parameter called as a propagation constant, and for the second order differential equation you can find out the solution. So here with respect to the voltage, if you observe, which is d square v by dz square minus gamma square into v of z equals to 0, indicating the solution of the second order differential equation will be having two components. One is first component is called as v plus e power minus gamma z, indicating the incident wave or wave traveling in positive z direction. Minus gamma, it is a attenuation propagation constant, and plus z indicating the wave is traveling in positive z direction, that is from source to the load. And another component which you have is v minus component, we call it as a reflected wave with a magnitude as v minus, and the propagation is in negative z direction, e power gamma z, minus gamma into minus z, which gives you gamma z, wave traveling in negative z direction. Similarly, the second governing equation, if you consider second order differential equation, which results in minus d square I by dz square minus gamma square I equals to 0. If I find solution, same way you'll have two components. One is incident wave, another one is reflected wave. And in the diagram also you can observe when the wave travel means I of z, which we are considering a section of transmission line of length L, and you can represent. And you can observe the new parameter which has come into picture here is a propagation constant, which is gamma, which is square root of z into y. So z is r plus j omega l and g is j plus j omega c. And as it is a complex quantity, you will have both real part and imaginary part. Real part is nothing but attenuation, and imaginary part representing phase shift constant. And for a lossless line, if I consider r equals to z equals to 0 in case of lossless line, the same propagation constant will result in only will have only imaginary part. The real part will become 0, no attenuation. Uh, uh, the same thing which we have seen here, given a transmission line, expressed that governing equation, writing a governing equation d square v by dz square equals to z into y, which is nothing but gamma square into v, where gamma square is z into y. Gamma, if I want to determine, is the square root of z into y, and will be having that as a complex quantity. You'll have a um, magnitude and phase. So alpha we call it as attenuation constant, beta is we call it as a phase shift constant. So this second order differential equation will have a solution as consisting of two components. First component a into e power minus gamma z, b into e power plus gamma z. This consisting of incident and reflected wave, and that is a solution. And now we will consider how the traveling wave attenuates once if it propagates through a section. So forward traveling wave which we are considering, so that means wave is propagating in positive z direction. So that means if I consider a t equals to 0 and the wave is propagating in positive z direction, and you can observe v plus of z indicating that is wave traveling in positive z direction. We'll have a magnitude as v naught and uh, v naught into e power minus gamma z. Now gamma is nothing but alpha plus j beta. So expand, so you'll have alpha component and you have a beta component. And we know that it is varying only with respect to the space. If I express in terms of time also, so consider the same along with space, along with time variation into e power j omega t. So now in this case, take a real part of that v naught plus, that is a magnitude, and consider all the let us consider v naught plus has a initial phase which is represented as e power j5. So v naught plus into e power j5 into e power minus alpha z into e power minus beta z into e power j omega t. So real part, no, as we know that e power theta, j theta can be represented as sin theta plus cos theta divided by 2 cos theta plus j sin theta divided by 2. So real part we are considering, that means you'll have a cos theta part. You can represent that as v naught into e power minus alpha z, considering the remaining part as e power real part of that considering as cos omega t minus beta z plus phi. And here you can observe v naught e power minus alpha z representing magnitude of the wave will keep on reduces exponentially as time progresses or as space progresses. So you can observe here v naught into e power minus alpha z. And the other term which accounts for the phase variation. Phase variation you can observe here. Phase variation you will have with respect to the time and with respect to the space and the initial phase. So omega t phase variation represents with respect to the time, and beta z represents phase variation with respect to the space, and phi representing it is a initial phase. So and you can observe beta is nothing but 2 pi by lambda. So it repeats after every 2 pi. Beta lambda it repeats after every cycle. So beta you can calculate from that, which is 2 pi by lambda. And, in the same manner you can also represent the reflected wave also. So now we will consider the phase velocity, the velocity with which the wave is traveling. For that, let us consider, take a velocity of a fixed point of the wave. That is, for example, on the wave crest we are finding. So phase velocity I wanted to determine, so which is nothing but v plus of z comma t, just now as we had seen expression. In that expression I need to maximize phase velocity I wanted to determine. So omega t minus beta z will become a constant. So I differentiate this equation with respect to time, which gives you omega minus beta dz by dt. Constant differentiation it becomes 0, and dz by dt I wanted to express, which is nothing but velocity. You can rewrite the expression which gives you omega by beta. Or you can also represent, we know in general velocity is nothing but delta z by delta t, distance by time, and omega, which is nothing but angular frequency indicating a variation of phase with respect to time, so which is delta phi by delta t. Units of angular frequency, meters per second, sorry, angle per second. Similarly, beta, if I want to express, which is nothing but representing the variation of phase with respect to space, or delta z. So delta phi by delta z, and angular frequency represents variation of phase with respect to time. Phase constant, beta value represents a variation of phase with respect to space. So now you rearrange these two equations to get a velocity. Velocity as v is equal to omega by beta. If you represent, then delta phi by, you'll get delta z by delta t. Or you can also express from this equation. So phase velocity, from this we can conclude, which is the ratio of angular frequency omega to phase constant beta. And the same thing can also be expressed omega by beta in terms of root LC1. You substitute for beta, which is 2 pi by lambda, and you can express. Okay, before we express Vp in terms of L and C components, we'll see one more parameter called as a characteristic impedance. So characteristic impedance is the impedance measured at the input terminals of a transmission line when the length of the transmission line considered to be as infinite. I repeat the statement. Characteristic impedance is the impedance measured at the input terminals of a transmission line when the length of the transmission line is considered to be an infinite. So at the input terminals, ratio of voltage to current, which gives you the impedance. When the wave is traveling in positive z direction, you can consider z naught value as v plus divided by I plus of z. Actually, it is a number, it is not a function of z. We can represent v naught plus by I naught plus. So I wanted to determine what is this IV plus of z and I plus of z. We know that it is the one when the wave is traveling in positive z direction, incident wave, amplitude with a phase can represent as v naught into e power j minus gamma z. Similarly, for the current, I naught plus into e power minus gamma z. Take ratio of that. Before you take a ratio, you rearrange the expressions and to get v naught plus to I naught plus ratio. So for that, we know the governing equation. In the governing equation, we know that dv by dz is nothing but minus z into I. Now in this equation, you dv by dz, differentiate this voltage equation. Differentiate that voltage, which is nothing but v naught e power minus gamma z. If I differentiate, you'll get minus gamma into e power v naught into e power e minus gamma z on the left hand side. On the right hand side, minus z. What is I value? I value is nothing but I naught plus into e power minus gamma z. Now take a ratio of v naught to I naught. So if I take v naught to I naught ratio, e power minus gamma z on both sides, which will get cancelled, and minus which will get cancelled. V naught to I naught ratio you'll get as gamma. If I send this term to here, minus z by gamma. What is z? Z is r plus j omega l. Gamma is nothing. Z by gamma. Gamma is nothing but square root of z into y. So if I take a z as square root of z into square root of z, cancels, left out with square root of z by y. Or you can say that the characteristic impedance, it is a ratio of voltage to current ratio at the input side, and it can also be expressed in terms of series impedance and shunt admittance as square root of z by y. Z is r plus j omega l and y is g plus j omega c. So here you can observe lossless line. We can calculate the characteristic impedance. You can calculate as make r value g value 0, which will give you j omega l by j omega c square root. J omega cancels. You will have z naught value as root l by c. Let us consider a problem. In this problem, they had given you the parameters as resistance, capacitance, conductance and inductance values. All these are varied with respect to space, and that means distributed parameters per unit length. And they're specifying the transmission line is operating at 1 gigahertz. And what they're asking you to calculate, they're asking you to calculate the characteristic impedance. It is the impedance at the input terminals. And they're asking you to calculate the propagation constant, so gamma value. And the last part, they're asking you to evaluate both characteristic impedance and the propagation constant, assuming that the line is lossless. Lossless case, as we know, gamma will become only j beta, that is j omega root LC, whereas z naught will become square root of L by C. So just substitution and determining the values. So z naught, if I want to evaluate from the basic formula, which is square root of z by y, which is r plus j omega l by g plus j omega c, r value given, which is 2 plus j omega. Omega is nothing but angular frequency, which is 2 pi f. So 2 pi f is 1 gigahertz, which is 10 power 9. Substitute the value of l and remaining values are substitute, and as it is given in square root, magnitudes you can take a ratio and taken a square root. And angle you have, no, so when it is under the square, means a division, during division, as we know, you can subtract angle a divided by angle b. If I have, you will get angle a minus b. But under square root you have, no, so that under square root, if you take some angle, it will not be direct square root. You need to take it as half of that. Okay, so you can convert that into a polar form and polar to rectangular form, normal conversion. Similarly, gamma value you can calculate, which is propagation constant, as square root of r plus j omega l into g plus j omega c. You just substitute the values and determine the value of the propagation constant. And here you can observe, which is a general case of wave propagating in positive z direction, representation with respect to space and with respect to time and space. So first one, representing with respect to the space only. So total voltage will be a sum of two parameters. One is the incident wave of traveling in positive z direction and the reflected wave traveling in negative z direction. You expand gamma value, which is alpha plus j beta, so minus alpha z into minus j beta z, and consider v naught plus will have an initial amplitude and initial phase shift as v naught plus and into e power j5. Similarly, for the negative reflected wave traveling in negative z direction. This is the case considering only space variation. If I consider the same thing with time variation, you will have the component as real part of v of z into e power j omega t. So consider the amplitude part and the phase shift part. In the under phase shift, as just now I've specified, you have an angular with respect to the time phase accounted, and with respect to the space phase accounted, and the initial phase shift. So omega t minus beta z indicating wave traveling in positive z direction. Omega t plus beta z indicating wave traveling in negative z direction. So you remember, when you give an input signal, uh, and as it is passed through a transmission line, we will have two components. One is incident wave and the reflected wave. So incident wave with respect to time and space, if I represent, will have attenuation and phase constants. So the phase shift accounted when wave travels through the line to be accounted for. So, and the characteristic impedance already we have, which is nothing but the ratio of voltage to current. And in general, the voltage and current equation, you can observe major difference is you can express current in terms of voltage also. I plus, you can represent wave current positive traveling in positive z direction, which is V naught by Z naught. But the reflected wave, the direction of the current as it is in reverse, so that's why minus you will get here in the current equation if I express it in voltage form. So V naught minus V naught, V naught of minus by Z naught. Okay, the reference current directions were in opposite direction. That's the reason why here you will get negative. So voltage equation and current equation, solution of second order differential equation. So this is just a summary of what we have done till now. So VZ voltage equation, if you consider a transmission line of length delta Z, then the voltage equation will have an incident and reflected wave, and current you'll have a incident and reflected representing in terms of voltage, and you have got a new parameter called as R gamma, which is alpha plus j beta, or you can also represent as square root of z into y. And we have derived for z naught, which is square root of z by y, and we have defined the guided wavelength, beta into lambda, which changes for every cycle, r lambda if I want to determine to pi by beta, or beta if I want to determine to pi by lambda. We have derived one more parameter called as a phase velocity, which is a ratio of omega to beta. This is a summary of transmission lines, what we had seen, and the same summary we can conclude for lossless case. Lossless case indicating where resistance and conductance will become 0. So gamma factor will become, by making R value Z value 0, you will have only j omega root LC. So alpha value becomes 0, only we have beta term, and phase velocity will become omega by beta, and omega by beta, from this you can represent as 1 by root LC from this equation. You can say that phase velocity in this case now, it is independent of frequency. It is not varied with respect to the frequency. Only L and C values will determine phase velocity. In the same manner, if I want to determine the characteristic impedance, R value, G value substitute 0, will be left out with square root of L by C. It is independent of frequency. It is only a real part in case of lossless line. So this is about um, transmission line analysis, governing equation, then followed by few solution of governing equation, voltage and current, and characteristic impedance derivation, then derive the same for lossless case. Thank you. Thank you.